Welcome back to the Deep Dive. Today, we are definitely moving past Regression 101.
We are.
We're going to take the absolute bedrock of statistical modeling, the general linear model, and really push it into the complex, curved and messy reality of real-world data.
That's right.
Our mission today is to upgrade your understanding from just fitting simple straight lines to handling true data complexity.
And that's so important because our sources today are all focused on this one core truth. In the wild, relationships are almost never perfectly straight or just simply additive.
Right.
This deep dive is all about understanding the tools you need to correctly model those curves and those interdependencies.
Okay, so before we jump into the curves, let's nail down the foundation. We keep calling this the general linear model, or GLM. If the data is curved, how can the model possibly still be called linear?
That is the essential and I think kind of counterintuitive definition we have to start with. A model is linear if the parameter, exactly, the coefficients, the betas, if they all have an exponent of 1. We are only concerned with the linearity of the coefficients.
Okay.
The independent variables themselves, they can be squares, cubes, really complicated functions of your raw data. As long as those beta coefficients are linear, you are still operating within the GLM framework.
That's a great distinction. So if the relationship isn't straight, isn't simple, how do we add that complexity? We need tools for curves, for interdependent relationships, and then for figuring out which variables even matter.
Yep.
Let's start with curving the line.
Curvilinear modeling is where we begin. You use this when you see the impact of a variable changing as that variable increases. Maybe the effect accelerates or maybe it, peaks and then reverses.
I'm thinking of something like stress level versus job performance.
Perfect example.
I can picture that in my head. Too little stress, performance is flat. You hit that optimum stress, performance peaks, and then with too much stress, performance just collapses.
That's a classic inverted U shape.
So how do we build that shape into our linear equation?
We simply introduce a squared term. It's called a second order model. So if you're looking at one predictor, let's call it x1, you just add x1 squared.
So the formula is now.
It becomes y equals beta 0 plus beta 1 times x1 plus beta 2 times x1 squared plus your error term. And the key thing is we just treat that x1 squared as a totally new variable in our model setup.
And what does that beta 2 coefficient, the one attached to the squared term, what does that tell us about the curve itself?
Beta 2 is the quadratic effect. If beta 2 is positive, the relationship is U-shaped. So y starts increasing slowly, but then it takes off and increases at an increasing rate.
And if it's negative?
If beta 2 is negative, you get your inverted U-shape, like that job performance example. The positive effect of x1 diminishes, it hits a maximum, and then the effect actually turns negative.
Okay, here's where it gets really interesting for you, the listener. It means the slope, the rate of change, is no longer constant.
It's not.
You can't just say a 1-unit increase in x always does z.
Exactly. The marginal effect of x1 on y is now a moving target. If we calculated the rate of change, we'd see the formula includes x1 itself, which means the slope changes entirely depending on where you are on that curve.
You have to know the value of x1.
You have to specify the current value of x1 to describe the effect.
Okay, that covers curves. Now let's talk about when two variables are sort of dancing together, interaction effects.
Right.
This happens when the effect of one independent variable on your outcome depends directly on the value of another independent variable. It's like statistical synergy.
Or conflict.
Or conflict, yeah.
Yeah.
And to capture that interdependence between two predictors, say x1 and x2, we have to include a new term that's just them multiplied together, x1 times x2.
So the model gets another term.
It does. It becomes y equals beta 0 plus the main effects plus beta 3 times x1, x2, and the error. That beta 3 coefficient, that's what measures the interaction.
Our sources had a fantastic case study with Tyler Personal Care. They looked at how sales were impacted by price and advertising.
Oh, yeah. And the interaction effect there was just, it was profound.
It was a perfect demonstration. They compared the change in sales when advertising went up by $50,000. And if the price of the shampoo was low, say $2.
Right.
That extra advertising drove a huge mean sales difference, 347,000 units.
But then, if they ran the exact same ad campaign when the price was high, maybe $3.
That sales boost just plummeted. It was only 43,000.
Why?
The effect of pouring money into advertising practically disappeared when the product was already expensive. The variables clearly weren't just adding up, they were counteracting each other.
And the estimated interaction coefficient for that was minus 6.08. That negative number tells the whole story, doesn't it?
It confirms that diminishing return. Since the coefficient is negative, a 1-unit increase in advertising expenditure decreases the effect of price on sales by about 6 units.
So they're tied together.
The effects are interconnected. The marginal effect of price on sales is no longer fixed. It's completely dependent on how much money you're sinking into advertising.
The implication is massive. You can't meaningfully talk about the effect of price without knowing the current level of advertising.
Exactly. You only understand the full relationship when you analyze them together.
Okay, so we've modeled these tricky relationships, the curves, the interactions. But what happens when the data itself is messy? Or the model violates those core assumptions? When your residuals start forming that widening funnel, that wedge shape, that's a problem, right?
That wedge shape is a classic sign of heteroscedasticity.
Right.
Which is a fancy way of saying the variability in your errors is increasing as your predictor variable increases. That violates a key assumption of regression. And this is where transformations become indispensable.
Transformations like logarithmic, square root, reciprocal, they're a structural fix. How do they help with that wedge problem?
They often compress the dependent variable. They smooth out those extreme high values. We saw this with the MPG and car weight example.
Oh, right.
The initial model had that obvious wedge-shaped pattern in the errors, but by taking the natural logarithm of the dependent variable, so ln MPG,
okay,
the variability became uniform across all weights. The wedge just disappeared. The model fit became excellent.
So that's a transformation for fixing error assumptions?
Yeah.
But they're also a kind of secret trick for making nonlinear models solvable with standard techniques, correct?
Absolutely. Think about an exponential growth model, which is nonlinear. Something like e of y equals beta 0 times beta 1 to the power of x.
Tough to solve?
It is. But if we take the natural logarithm of both sides, it suddenly converts that exponential model into a linear equation. You get the log of e of y equals the log of beta 0 plus x times the log of beta 1.
And now it looks like a normal regression equation.
Now you have a linear model. You can use standard regression tools, solve for the log values, and then you just exponentiate the results to get back to your prediction.
This logarithmic trick is powerful, but it comes with a huge warning label, doesn't it?
A major caveat.
The interpretation of the coefficients changes completely. We're not talking about simple unit changes anymore.
You have to be extremely cautious here. For example, in what's called a log-level model, where you log the dependent variable y, but x stays the same, the meaning of beta 1 flips from a unit change to a percentage change.
Okay. Give us the breakdown on that interpretation.
So if you look at that beta 1 coefficient in a log-level model, a 1-unit increase in x results in a 100 times beta 1% change in y.
Can you make that practical?
Sure. Let's say you're modeling stock returns, and beta 1 for an analyst rating on a 1 to 5 scale is 0.05. That means increasing the rating by 1 point does not increase the return by 0.05. It increases the expected return by 5%.
And that difference is enormous for any business decision.
It's night and day.
That context is just crucial. So we now have the tools to model complexity and fix our data. But the final hurdle is deciding what to keep and what to discard. How do we build the ultimate, most predictive model? We can't just chase the smallest p-value.
You hit the nail on the head. Variable selection requires 2 criteria. Statistical significance, which is the p-value, telling us about reliability, and effectiveness.
Effectiveness being?
The practical impact, which we usually assess by the increase in adjusted R-squared.
And our sources have these 4 scenarios that just perfectly illustrate this balance. Let's walk through them because this is the difference between a statistically correct model and a truly useful one.
Okay, scenario 1. Significant and effective. This is the dream. Adding age to predict blood pressure. You get a tiny p-value, less than 0.01, and the adjusted R-squared jumps from 0.3 to 0.45.
Reliable and meaningful, you keep it.
Definitely keep it.
Okay, scenario 2. Significant but not effective. Imagine adding, say, hair color to a huge model predicting income. You might get a significant p-value, maybe 0.02, because your sample is huge.
Right. With big data, you can find significance everywhere.
But the adjusted R-squared barely moves. It goes from like 0.25 to 0.251. The effect is too tiny to matter.
Then the reverse of that, scenario 3. Effective, but not significant. Hours of sleep predicting student performance might increase your adjusted R-squared a lot, say from 0.4 to 0.5.
A huge impact.
A huge impact. But the p-value might be weak, maybe 0.08. So you have a meaningful effect, but you lack the statistical support. You probably need more data.
And the easiest one, scenario 4, neither significant nor effective.
The easiest call.
Adding shoe size to predict customer satisfaction.
High p-value, adjusted R-squared probably goes down. You exclude it without a second thought. And we can also use a formal F-test to compare models. If you add a group of variables, the F-test checks if the reduction in the total unexplained error, the SSE, is significant enough to warrant making the model more complex.
Right, like in that Butler trucking example.
Exactly. Adding that second variable, x2, it reduced the SSE by a very significant amount. It easily justified its inclusion.
That makes sense for a handful of variables, but if you have dozens of potential predictors, you can't test every combination by hand.
It's impossible. This is where we need semi-automated procedures, methods that rely on entering and exiting thresholds.
Let's start with stepwise regression. What's this unique mechanism?
Stepwise is iterative. It alternates. First, it checks if any variable currently in the model should be removed, if its p-value is too high. Then it checks if any variable outside the model should be added because its p-value is low enough.
So it's constantly cleaning house and restocking the shelves. What's the fundamental limitation of that?
The limitation is that it's not exhaustive. It's a greedy algorithm. It only considers the best move right now. It does not look at all possible combinations of variables.
So it doesn't guarantee the absolute best model.
It finds a good model, but maybe not the optimal one.
And then we have the two one-way streets. First, forward selection.
Forward selection starts with an empty model, and it only adds the single most significant variable one at a time. The restriction is rigid. Once a variable is in, it is permanently locked in.
It can't be removed later.
Never, which can cause issues if a variable added early becomes redundant after a more powerful one is introduced.
And it's opposite, backward elimination.
Backward elimination starts by throwing every single predictor into the model, all of them. It then works backward, removing the least significant variable at each step.
And the same restriction applies.
Same restriction. Once a variable is removed, it can't re-enter, which can also lead to a suboptimal result.
So if none of these three iterative processes guarantee the best model, how do analysts find the global optimum?
For that, you use best subsets regression. This isn't iterative, it's exhaustive. It evaluates all possible subsets for a given number of predictors. So it finds the best one-variable model, the best two-variable model, and so on.
And it just gives you a ranked list.
It ranks them, usually by the highest adjusted R-squared, giving you a comprehensive menu of the trade-offs between simplicity and fit.
This has given us such a powerful and robust toolkit today. We've covered designing complexity with interaction terms, fixing bad data with transformations, and then finally using structured methods to choose our final variables.
What's fascinating here is that reliance on automated methods really reveals a tension in data analysis. We established that the popular methods, stepwise, forward, backward, they're efficient at finding good models quickly.
But they can't guarantee finding the best model.
They can't because they don't look at every combination.
So this raises a core question for anyone building models.
It does. When you see that these different procedures give you slightly different results, how much do you rely on their statistical shortcuts versus integrating deep theoretical justification or, domain knowledge to guide your final choice?
That's the art of it.
The real expertise lies in combining the efficiency of automated methods with the insight of what our sources call Strategy 10, using theory to guide which variables should enter or exit, regardless of what the p-values say in the middle of the process. That critical combination is the key to building models that don't just predict, but truly explain.
An excellent thought. That's something to mull over as you build your next model. Until next time, keep diving deep.